All right, so let's go ahead and talk about titration. These are the questions that everybody's been asking me. How do I do these, Mr. Crandall? I keep saying we haven't got there yet. So let's get there, okay? So titration is simply the process of being able to calculate the concentration of an unknown acid or a base using the known concentration of its reciprocal, okay, or of the other of an acid or a base, okay? So if this is an acid, this purple stuff right here, if it's an acid, okay, and I want to determine its concentration, the concentration of that acid, well, if I understand this reaction, okay, an acid plus a base produces water. So if I have a known concentration of base, okay, so let's say it's 0.5 molar sodium hydroxide, okay, and I put that into this burette right here. So the blue stuff, let's say, is the sodium hydroxide. It's the base, okay, and this down here is the acid. It's of unknown concentration. So for every time I add some of this base to this acid, the acid will neutralize the base. Okay? And the pH is going to begin to change. So this eventually will completely change until the indicator that's inside of the flask turns pink, which I guess maybe that's pink, not purple, until it turns pink, because the indicator is pink at that neutral pH or at a basic pH. So it was acidic, it's clear, and then when you reach that basic pH, it goes pink. Okay. Now there's all kinds of indicators, and if this is acetic acid, let's say, then you have to choose a indicator that will show you the color change at the correct pH of neutralization. And the reason I say that is because not every acid or base neutralizes at a pH of 7. Okay, you're like, well, yeah, it does, Mr. Crandall. Isn't that the neutral pH? Yes, that's the neutral pH. But for other reasons, apart from complete neutralization, when you neutralize something like acetic acid, CH3COOH, okay, when you neutralize it with sodium hydroxide, let's say, it's going to become sodium acetate plus the neutral water, because you neutralized this hydrogen with this hydroxide. Okay? But what's left over? What's left over is a weak base. And a weak base creates an equilibrium, meaning that this thing is not going to just stay put. It's going to go CH3COO minus plus H2O to produce CH3COOH plus OH minus. Yeah, this is going to happen after you neutralize it. This will happen. At neutralization, this process right here will happen, and the pH of your solution ends up being what? Acidic or basic? Basic. So I don't choose an indicator for acetic acid that's a neutral indicator at pH of 7. I choose it for a basic indicator at a pH of 8 or 9, because that's what this ends up being when it neutralizes. Okay? So, and we're going to see that for some of these. So, but the indicator will turn pink at the neutral pH if you choose the correct one for whatever you're using. Now, if this was sodium hydroxide and you're titrating HCl, hydrochloric acid, then yes, it's going to go completely neutral because what's left over after that is sodium chloride plus water. And sodium chloride does not establish an equilibrium in solution between its conjugate acid and base to create an acidic or a basic pH after the neutralization. It just stays neutral. This is a pH of 7 will be where this ends up at neutralization, the equivalence point. Okay. So here you can see an example of this happening. They're adding drops of the sodium hydroxide into the acid solution, and at the point of neutralization, it's going to turn pink. Okay, when we reach that, we're going to have that the color change. Okay, and we're going to do some of these. I think actually our next one's a titration, our next lab. If you guys are in the lab, we're going to take we're going to do a neutral acid-base titration. Okay, and so that's that point where you have neutralized everything. We call that the equivalence point. Okay, the equivalence point is the point at which you've neutralized all the acid and base, and that can be at different pHs for different solutions. Okay, so here are some indicators. So you can see how you have a lot of indicators that you could choose from. So for acetic acid, we would choose this one because it has a pH right there in the range that we want it to be. The color change is right there at that pH where we want it to be. So we would choose that one for acetic acid and say, okay, when it reaches its neutralization point, boom, that's where we can take it. Now, you don't only do titrations using indicators. You can also do titrations just simply by using a pH meter. And you check the pH over time, or with every addition of sodium hydroxide, you measure the pH, and you'll get a graph. And from that graph, you'll get a curve, something like this. And then you can find from that graph the equivalence point. That's the equivalence point right there in the center of this steep line. Okay, so we essentially have three lines here. One here, and one here. And the middle of this line right here is my equivalence point, which is the point between these two straight lines here and here. Okay, that's my equivalence point. That's when I've reached equivalence. So I can do that. I can graph it, and I can find my equivalence point. And you'll notice for different solutions, you're going to have an equivalence point at different pHs. Okay, some of them are going to be acidic, and some of them are going to be basic. So you can see these color changes happening in things like plants. These plants here. This one was grown in a pH of 5. Less than 5. And this one was grown in a pH greater than 5. You can see the color changes. Same plant. Another good one is red cabbage. So if you go to the grocery store, buy some red cabbage. You can create an extract of that. You just boil it. And the water that's left over, a lot of times is blue. So you have this blue water. And that's because there's basically a pH indicator in there. And you could use that in different solutions that are either acid or basic, and it would give you a whole color spectrum between like red to purple to green and blue and yellow. You would have this whole spectrum of colors that you could set up just by simply boiling some cabbage. In fact, I have some right here. This is some cabbage extract. I use it to show to set up those pH indicators. So it's really easy, easiest thing to make.
Is that how the Marquis test works?
Marquis test? I'm not familiar with that. Marquis test? Oh. I don't know. I guess it would depend on. I don't know. I don't know what they're looking for exactly. But I can't say that it's because of an acid-base indicator, because the drugs aren't necessarily acidic or basic. Maybe I would have to see which specific drug you're talking about and what. There's all kinds of assays that they could use. I mean, pregnancy tests change color, but they're not measuring acid or base. They're measuring for a hormone, and it's a very complicated process. That hormone causes this other reaction to occur in this other one, and then it causes a color change, right? So, yeah. It could be a lot of different things. So it could be that's just picking up the specific drug, finding it, which causes a chain reaction to something else, which causes the color change. So. Okay, so let's look at how we do titration calculations. Oh, we didn't go over that very well, did we? Let's go back here, and that was on this page. So right here, very simple equation. The moles of an acid times the moles, the volume of an acid equals the moles of the base times the volume of the base. This should look fairly familiar because we've had an equation just like this for dilution. M1V1 equals M2V2. That's the dilution equation. And if we're, that's because the moles of the original solution are equal to the moles of the new solution. And it's the same thing with the acid and the base. The moles of the acid are equal to the moles of the base. It's the same. Okay? So because the moles of the base here are going to determine how many moles of acid were in the solution. Okay? So we can use this equation to determine the unknown concentration of either an acid or a base. So if I know exactly how much base I added here during this titration, then I can do this. So if it was 0.5 molar sodium hydroxide, and I added if I added 27 milliliters of it, okay, then 27 times 0.5 will tell me the moles of the base. That's how many moles of base I added. Well, not exactly, because that's in milliliters. But, and that's a good point, because if I'm using this equation, and I'm using milliliters here for the base, then I just need to use milliliters here for the acid. Okay? But if I'm using liters, I need to use liters. Now, if I was going to calculate actually the moles of the base, I would have to do it in molarity, and therefore I'd have to change that 27 milliliters to liters. Okay? But if I'm just using this equation, I can leave it because it creates a ratio between the volume of the acid and base, and the units will cancel anyways, so it's fine. Or if I'm solving for the volume of the acid, then I can easily just keep it in milliliters and have my answer in milliliters. Okay.
So the volume, as long as the units are the same, it doesn't matter, and then of course moles for the acid.
Yes, if I was actually going to find the moles using the molarity equation, I would have to use liters. But if I'm just using this equation, it's the ratio that matters. If it's milliliters and milliliters, it's fine. If it's liters and liters, it's fine. Or I can solve for milliliters or liters. Either way, it will work. Okay, so I don't have to change it. So here, 27 milliliters of 0.5 molar sodium hydroxide. And let's say I was titrating 10 milliliters of an acid. So 27 times 0.5 divided by 10. That's how I would find the unknown concentration of that acid. So let's do a few practice problems here. Calculate the molar concentration of a sodium hydroxide solution if 25 milliliters of this solution were required to neutralize 45 milliliters of 0.3 molar HCl. So we have a 0.3 molar HCl solution. That's 45. We have 45 milliliters of a 0.3 molar. Okay. So MaVa equals MbVb. What am I solving for? Okay. The concentration of the sodium hydroxide, what is that? Ma, Va, Mb, Vb. What is it? Mb. Okay, Mb equals MaVa over Vb. Right? Okay, so the molarity of the acid is 0.300 molar HCl. The volume of the acid is 45.00 milliliters, divided by the volume of the base, which is 25.00 milliliters. Okay, you see how the milliliters cancel, so it doesn't matter. If I had changed that to liters, I would get the exact same answer. So it doesn't matter that whether it's in milliliters or liters because it's the ratio. 45 divided by 25 is the same as 0.045 divided by 0.025, okay, which would be the liter amount, right? So it's the same. Okay, so what is my base molarity? Okay, 0.54. So this is how I'm going to do these titration questions. Okay. Calculate the molar concentration of a KOH solution if 45.65 milliliters of the solution were required to neutralize 50 milliliters of 0.1 molar HNO3. Okay, try to set that one up, and then I'll set it up in a second. Make sure you're doing it right. Okay, so is this what you guys were doing? Same equation, it's basically almost the same question. Okay, so this is the molarity of the acid times the volume of the acid divided by the volume of the base will give you the molarity of the base. Okay. What'd you guys find? 0.1 times 50 divided by 45.65? 1095?
Yeah.
So because it took almost the same amount of acid as you had base, it does come out to be very similar concentrations. Okay, if it was exactly 50 down here, right, it would be exactly the same molarity. Yes?
We're not finding the MA?
Not in those ones. Here, this is sodium hydroxide. Calculate the molar concentration of sodium hydroxide, which is the base.
So the second question.
This one is calculate the molar concentration of potassium hydroxide, which is a base. Okay, so but you know what? It doesn't really matter whether you would have set it up as the acid or the base. You would have found the same answer.
But if it is an acid, then we put MA.
That's right. Okay. Calculate the molar concentration of sodium hydroxide solution if 25 milliliters of the solution were required to neutralize this amount. Okay, so we would set that up almost in the same way. You can see that there's not a whole lot to this. Usually we're always trying to find either MA or VA. It's possible you could get some questions thrown in there like what is the volume of base that you would need, or what is the volume of the acid you would need to neutralize this amount from this thing or something. Okay, so that's a possible type of question, but if you're doing a titration, the idea is you're trying to find the molarity. So the equation is going to be essentially you're looking for the molarity and acid of, or base of, the molarity and volume of the acid or base divided by the acid or base. Okay, so it's almost always the same thing. So if you always look for the pair, you essentially multiply those divided by the other. That's how you're going to do these. Divide it by the loner. The pair, multiply them together, divide by the loner. Okay? And that's how it is in almost all of these questions. You find the pair. Here's that pair. Here's this pair. You find the pair, multiply it, divide it by the loner. Okay? That's how these are going to essentially be. Calculate the molar concentration of a potassium hydroxide solution. Okay, and good, we came out to that, right? That's where we found it to be. Now, polyprotic substances means that you have an acid like H2SO4. And H2SO4, if you notice, has two hydrogens associated with it. So that makes it a little different when you do the calculation for the concentration here. Okay? Because what we were just doing, we were finding the calculation based on a 1-to-1 ratio. One acid for one base, right? But here, that's not exactly the case. Look at this equation. Two bases for every one acid, or one H2SO4. So if I want to know the concentration of H2SO4, not the concentration of H+, but the concentration of H2SO4, then I essentially have to divide it by 2 when I find it. When I find the concentration of H+, well, there's 2 H's here for every one H2SO4, so I would have to divide it by 2 to really find the concentration of this H2SO4. Okay? After the titration, because the titration is going to neutralize both of these hydrogens. That sodium hydroxide is going to pull them both off, get rid of both of them. Okay? And so if I was titrating an H2SO4 solution, I would need to remember that stoichiometric relationship. 1 H2SO4 for every 2 sodium hydroxides. Okay? So then when I found the H+ ion concentration, I could convert it to the H2SO4 concentration from the H+ concentration, knowing that for every 2 H+'s, I have 1 H2SO4. It's just a stoichiometric relationship. Okay? So once I find the moles of H+, I can easily find the moles of H2SO4 in the same way. And you can just do it in molarity. You can just leave it the molarity of the H plus, molarity here. Okay? So if this was 2 molar H plus, then it would be a 1 molar H2SO4 solution. This would be 1 molar H2SO4. Any questions about that? For some reason you guys look kind of confused about it. You are? Okay. So look at this balanced chemical equation here. How many hydrogens are on this H2SO4? 2. So when I do a titration, I will neutralize both of them, right? Because look, I'm just going to be left with sulfate and then the water. Both of the hydrogens were neutralized, right? So but I get 2 hydrogens for every 1 H2SO4. Okay? So if I do MaVa equals MbVb, it's not accounting for that this is H2SO4. This equation does not account for that. Okay? So if I solve using that equation, I solve for the molarity of the acid. When I find it, I then need to do one final step, one final conversion to the molarity of H2SO4 from the molarity of the acid. So for every 2 molarity units of acid, I have 1 molarity unit of H2SO4. Still not. Okay? So if it was 2 molar, if I determined this to be 2 molar acid, then it would be 1 molar H2SO4. I don't know if we do we don't really do any, let me see.
So this basically is referring to these that are like in equilibrium where they're not dissociating completely, right?
Most acids are monoprotic acids with 1 hydrogen that comes off. Most acids.
Oh, okay.
This acid, H2SO4, has 2
So
hydrogens.
it's the 2 hydrogens, that's the key.
Yes.
Okay.
If it's H3PO4, you have 3 hydrogens that come off for every 1 H3PO4. So I can easily find out how many hydrogens there are, but that's not going to tell me how many H3PO4s there are, what the concentration of the H3PO4 was. So once I find it, I then have to change it from the molarity of the acid to the molarity of H3PO4, knowing that there are 3 acids, hydrogens, acidic hydrogens, for every 1 H3PO4. Okay? So I can still use MaVa equals MbVb to find this, but that's not my final answer because this is H3PO4. It's a polyprotic acid. So I just have to give my final step. It could be. I would say, is it going to be a big part? No. You might get like maybe 1 question or something like that about that. But it would not be. I mean, just look at it. If it's a polyprotic acid, then you're going to have to calculate the final concentration, knowing that that your original calculation using that MaVa equals MbVb back to what it is. Okay, I will try to find an example for next time. Okay, we'll work out a problem, but I don't have any. Okay. So, chapter 6. I think you guys will like chapter 6. Not too bad.
We're actually done with chapter 4.
You're lying. I'm just in part 2 of chapter 4.
Okay, so I like chapter 6. I guess maybe that's what I mean. Whether you guys will or not, I don't know. Okay. So electron structure and the periodic properties of elements. So we're going to look at in this chapter where the electrons are located on these atoms. And so here we're gonna look at first try to understand light energy. What is it? Okay, so this is the electromagnetic spectrum, and as you move across the electromagnetic spectrum, you can see that the wavelength is very large over here. Okay, this is in units of, what is it, nanometers. Okay, 10 to the 12th nanometers. That's a big thing. That's 10 to the 12th is pretty large. Okay, all the way over here to gamma rays, which can be less than 10 to the negative 2 nanometers. A nanometer itself would be microscopic, so at 10 to the negative 2 nanometer would be very, very, very tiny. Okay, so this is the spectrum, and you can also see that energy here has kind of a different, an inverse relationship to this. So you have a big wavelength, but compared to the energy, look over here. The energy is large over here, and it's smaller over here. The wavelength is large over here, and it's smaller over here. That's because when we talk about a wave, okay, if I have a wavelength like this, the wavelength is measured between 2 points on the wave that are the same. So if I come here to this point and here to this point, that's the wavelength, or here to this point and here to this point, that's the wavelength. Doesn't matter, the same length, right? But that's the wavelength. This wavelength is smaller than this one. Are we agreed? Okay? So if I am measuring how many waves pass this point right here per second for this wave or for this wave, which one is going to have more wavelengths per second pass?
The shorter one?
Shorter one. That's called frequency. Frequency is measured in hertz, which is simply the units per second, meaning basically wavelengths per second. But you don't have a wavelength unit, so there's no wavelength unit there. So it's per second is your hertz, which is frequency. This has a larger frequency than this. So I have more penetrating wavelengths here than I do here. That means more energy is penetrating here than it is here. Higher energy, lower energy. Just like we see here. The bigger the wavelength, the lower the energy. So this is electromagnetic radiation. Radio waves are electromagnetic radiation. They have very long wavelengths. So they have very small energy. So we broadcast them everywhere. We don't care. They're not going to hurt us. They're not going to bother us. Right? You turn on the radio in your car, you hear there's all kinds of radio stations everywhere. So there's radio wave frequencies flying all over the place everywhere. Okay? But we don't care because the energy of that is so low, big deal. Okay? Microwave. Then you get to the microwaves. Infrared is lower than even visible light. Visible light spectrum is from 750 nanometers to 400. Okay? So you can see the wavelength is decreasing. Which one has more energy, red light or blue light? Blue light has more energy because it has a smaller wavelength. So blue light is right before you get into ultraviolet. Ultraviolet light can actually be damaging to your DNA and to things. So, in fact, in industry, if they want to sterilize something like plastic, they're not going to boil it. So they put it under some ultraviolet radiation, and they kill all the bugs that are in there using ultraviolet radiation. Okay? So that's a form of sterilization because it is high enough in energy that it will kill stuff, little bugs and things, okay? Bacteria and so forth. So once we start getting here, now we're getting worried, right? Because here we live in this. We live in the visible light region. So yes, we're getting exposed to that radiation all the time, but our bodies can handle it. But above that, now it's getting concerning. Now we're concerned, okay? So we have to be more careful. Up here in X-rays and then gamma rays, the worst kind. Okay? So the wavelength is getting really small here, and the energy is getting really high. Okay. That one kind of got in there. Let me see. We'll come back to that. So here you can see the light being split into its different wavelengths through this prism, right? Because the light right here, this white light, it's basically all of those, the whole spectrum of the light. It's just all combined. And so you can actually separate them out into their different wavelengths if you wanted to. Now, there was a scientist named Bohr. And Bohr wanted to understand this concept of where the electrons are on the atom. I think we might have talked a little bit about this earlier in the semester. But he developed a model, okay, that helped us understand positions of electrons on the atom. So here I have a nucleus, and surrounding that nucleus are energy levels. Energy level 1, energy level 2, energy level 3. Okay? And Bohr wanted to know, where are the electrons on this atom? Okay? And so what he did was, using electromagnetic radiation, he would shoot energy at these electrons, and he would excite them. And they would move up to an excited state. See, it's absorbing energy and it's moving up here. And then it would relax. And as it relaxes, well, it can only relax if it releases that energy that it absorbed. So when it releases that energy, we can measure the energy released. We can't measure the energy absorbed by the electron, but we can measure the energy released by the electron. And then, once you know the energy released, okay, because you can measure the wavelength and so forth of that energy, you would be able to identify the position of the electron on the atom in comparison to the nucleus. And that's what Bohr did. And he started to arrange the elements according to where the electrons were located, which actually helped us develop the periodic table that we have today. The periodic table is organized into groups based on where the electrons are on the atoms. Doesn't really look like it. That's how they're organized. And we're going to see how in a little bit. So this is just showing these the excitement of electrons. Gives you the in these neon signs or these noble gases. Okay, they would give you these different colors based on where the electrons are. And as they relax, that's the color you see. So our eyes are measuring the wavelength here, basically, because we can see different colors of light. Those are the electrons as they're relaxing. You excite the electrons, and as they're relaxing, they emit that light radiation. And that's what we see, is that light radiation being emitted by those electrons through that sign. Okay, fireworks, same way. These chemical reactions, as you burn them, they're releasing light. These metals, the metals, you excite the electrons, and as they relax, they release different colors of light, and that's how we see them. Okay, sodium salts, they give you a yellow burn or flame. Strontium give you a red flame. Copper salts would be blue flames. Calcium is orange, iron salts are gold, and barium salts are green. And then you get this spectrum of colors that you can create for these fireworks displays. Okay, so there's an equation that we use to calculate frequency and wavelengths. Go away. Okay, so this is the equation, the speed of light equation. C stands for the speed of light. All waves travel at the same speed, the speed of light. Because they're massless, they can do that. If you have mass, you cannot travel at the speed of light, because as you would approach the speed of light, you would get more and more dense, and as you got more and more dense, it would slow you down, and you could never actually get to the speed of light. But light itself is massless, and so therefore it can travel at the speed of light. So that's kind of the fastest speed achievable ever. 2.998 times 10 to the 8th meters per second. So it's very fast. This one? It says c, the speed of light, is equal to lambda v, which is your frequency. This is your wavelength. This is your frequency. Okay? So this is the speed of light equation. So we can calculate, using the speed of light, we could calculate the wavelength if we had the frequency, or we could calculate the frequency if we have the wavelength. Okay? So pretty straightforward equation. Okay? I could rearrange it. Basically, 3 questions here. What is, or actually just about 2. What is the wavelength, or what is the frequency? Wavelength is equal to c over frequency. Frequency. Okay? And frequency is equal to c over wavelength. And c is the speed of light, which is a constant. It never changes. Okay? Light travels at that speed. Whether it's a radio wave the size of a football field, or a gamma ray, which is very, 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 very microscopically tiny. Okay? Doesn't matter. They both travel at the same speed, the speed of light. Okay? Okay. The other equation, Nernst's equation, to calculate energy is energy equals h, which is Planck's constant, times the frequency. So alternatively, you could get another equation where E equals h, and if you replace frequency with speed of light and wavelength, times c over wavelength. Okay? Because frequency is equal to c over wavelength. So you could just replace it there. And then if they didn't give you the frequency, you could calculate the frequency and then calculate the energy. And this will be in units of joules. And that's because this is Planck's constant. 6.626 times 10 to the negative 34 joule seconds. Okay? So Planck's constant can be used to find that. Okay? Yes. Negative 34. So you can see here, we can easily find, if we know the energy, we could find the wavelength or the frequency. Because these two things are constants. They don't change. They're constants. Okay, so that only leaves us with what is the energy or what is the wavelength, or if we replace it here, what is the frequency. Okay, so which is essentially the questions we had earlier. What is the wavelength or what is the frequency? So here we just have what is the energy. Energy is equal to either this or this. What is the wavelength? If I want to find the wavelength, then I'm going to have hc over E. Or what is the frequency? Equals E over H. Okay? So essentially those are the questions that you could be asked. You could be able to calculate those given these constants. Okay? So basically simple algebra there, using Planck's constant to find.
What does Planck's constant represent then? Like
The energy per second. Or what do you mean?
well, the energy per second
Of a wave.
of a wave. Okay.
Of a wave. The energy of a wave. That's what it's representing. Yeah.
So this is SS?
I'm sorry?
SS or
J.
JS. Joules per second. Or not per second, excuse me. Joule seconds. Joule seconds.
Joules seconds. Joule. It's like
Joules
J.
times seconds.
Joules times a second. It's not over.
It's not per. It's not per second. It's joules times seconds. Okay?
So like on the top equation over here, you would be trying to figure out the energy of the wavelength then?
These ones,
No, over here.
this would be the wavelength itself. If you were given the energy and you want to find the wavelength, this is what you would use. So if they say this is how much energy is in this wave, okay, well what's the wavelength of it? Planck's constant times the speed of light divided by the energy. So I just needed to know that one thing, and I could find it. Frequency. Well, if I know the energy, I can find the frequency. Okay? If I know the frequency, I can find the wavelength. If I know the wavelength, I can find the frequency. And so this is all for just a wave. Okay? Okay. So here it's just showing kind of those distance traveled in 1 second. Okay? 4 cycles per second, 8 cycles. So you can see that more as you get a smaller wave. It's not that they're traveling faster. They're all traveling at the same speed. It's just that the wavelength is shorter for each one. Okay? Which changes that amplitude. Okay, here's just some guys just showing these devices. Radios, an ultrasound. So you go get an ultrasound, not a big deal, just using kind of radio wave frequencies. Okay? Cell phones are more up in here, this microwave region, radar, wireless internet, routers, microwave ovens. Okay? So people think microwave ovens are, they're like, oh, that's dangerous, right? You put something alive in there, it's going to explode. Not because of the radiation. It's because you boil it. You heat up the water. The water molecules become excited from that electromagnetic radiation that you're putting into them, and they absorb all that energy and they start vibrating, and they increase their energy to the point of they start to boil. So microwaves are tuned to water. That's why if you put something plastic in there, it doesn't get hot, right? Because the plastic doesn't absorb that energy. It's the water molecule that does. So you put something in there with water in it, and it's going to heat up the food because most food has some water in it. And so it will heat it up. So that's why some things heat up, but really the microwave radiation, it's not that big of a deal. It's lower than this radiation right here. The radiation from your microwave is less damaging than this radiation coming out of this light right now onto us.
But if you do, like they say, don't look at it. Have you ever heard that?
What? They say don't look at the microwave?
Don't look at it while it's going.
What? What are you talking about?
Yeah,
I have no idea where that came from. I've never heard that. But if you look at your microwave door, there's a screen on it. What that screen is doing, and it's absorbing all that microwave radiation, a lot of it. It's not even coming out. So, anyways, whatever. I don't know why they say that, but people, it could just be ignorance. I don't know, but really, look what the microwave oven is. The wavelengths of that stuff coming, it's no big deal. Okay, here it's less than your remote. Okay, night vision, and here's the visible light. You can see all this stuff is below visible light, so it's not that bad. Okay. X-rays though. A PET scan, cosmic rays, that's going to be gamma radiation. Or, when you guys think of a nuclear bomb exploding, you probably think of gamma radiation being released, and that's what's really bad about it. So the hydrogen bomb would be a cleaner bomb, wouldn't release as much radiation. But when they first started using it, yeah, it was massively destructive, but it didn't release a lot of radiation. So they're like, hey, let's put some, instead of just doing fusion, let's put some uranium in there as well, so that we can cause it to decay, and through radioactive decay, it will release some gamma radiations and be more deadly. So, because they were like, hey, this isn't deadly enough. It's just not. We blew up a whole city, but that's not enough. We need to irradiate everything around it and kill every living possible. Right? This is back in the day when they're first making these bombs. And
it's awkward when I went to the Hiroshima museum.
It's a different experience, huh?
Yeah, it feels shitty to see everything.
Yeah. Or to hear about like Bikini Island, and I don't know if you guys know about those kind of things, but it's just embarrassing, right? Yeah. Who is this America country we live in? Whatever. Okay, I'm not. Okay, but yeah. So, but that's mostly what you think about, this gamma radiation. That's the really deadly radiation that's going to come, and it's going to mutate your DNA and cause all this damage to you. Okay.
And that's the one that has a afterlife, it sticks around.
Depending on what has a half-life. So if something decays, like uranium, if it decays, it has a half-life. So its half-life could be hundreds of years. So if it has a half-life of hundreds of years, that radiation is going to be around for hundreds of years. If it's P32, and P32 has a half-life of minutes, then the radiation's gone within, a few minutes. So, but yeah, we chose some stuff that sticks around, right? So, okay, so here's actually the light spectrums of like sodium, hydrogen, calcium, mercury, and you can see the electrons positioning at different places based on the excitement and relaxation of them, and they're releasing that light energy, and you can measure it. Okay, so this is what Bohr was doing. Back to Bohr. Okay, so Bohr was measuring those positions, and he was trying to identify where the electrons were, kind of like this. Okay, so here, this color is purple. Oh, that's a negative 2.18 times 10 negative 18 joules of energy for one single electron, right? So a whole mole of electrons would be a whole different number. It would be a bigger number than that, okay? But that's what this is measuring. So you can position the electrons based on the light that's being emitted by them. Okay, so you can see some of them would get excited all the way up to here. They would relax, they'd relax back down to here. Okay, so that's how he would do this whole process. Okay, so he determined that as you move across energy levels, you're increasing in energy. It requires more energy to be in the second energy level than it does to be in the first energy level, or to be in the third energy level than it does to be in the second energy level of an atom. Now, our periodic table, if you look at it, do you see the numbering 1 through 7 down the side? That represents these energy levels. 1, 2, 3, 4, 5, 6, 7. So there are 7 what we call principal energy levels. 7 principal. Okay? 1, 2, 3, 4, 5, 6, 7. And we say n equals to identify them. N equals 1 is the first. N equals 2 is the second. N equals 3, the third, etc. Okay? So, if I'm going across the periodic table, I can identify the principal energy level for the representative elements. What I mean by that is these ones in the first 2 columns and these ones over here. Everything in the middle here, that's not true about. This is not in the 4th energy level. This is in the 4th energy level. This is not. This is in the 4th energy level. This is not. Okay? And we're going to learn why in a little bit. But our periodic table is showing us where the electrons are. But it's also showing us the energy associated with those electrons. The electrons for calcium are lower in energy than the electrons for scandium. Okay? So even though this isn't in the 4th energy level, it's still higher energy requirement. That's why it's placed after calcium. Okay? So with that, I am following my periodic table according to how they fill according to the energy associated with them. Okay? So these are my principal energy levels. Now, we call those rings around the atom, we call them orbitals because the electrons are orbiting. And within every principal energy level, there are sub-energy levels that create different orbitals. Okay? And we can identify those here. This orbital is S. These orbitals are P. These orbitals are D. And these orbitals are F orbitals. S, P, D, F. These are the sub-energy levels that are found within the principal energy levels. So we have principal energy levels, and we have within those principal energy levels, we have sub-energy levels. And those sub-energy levels have electrons orbiting in these fashions. If you are an S electron, you will orbit in a spherical fashion. You see how that's a sphere? That's how you're going to orbit the nucleus. You're going to create a sphere around it. Okay? You're just going to be orbiting around that nucleus. Filling up that. You could be found, essentially what it means is you could be found anywhere in that spherical space. That electron could be found anywhere in that spherical space. Now, here in a P, you can see that I take on a different shape on my orbitals. We call this a dumbbell shape. You take on the dumbbell orbital shape. Okay? The electrons for the P in the P can be found anywhere in this sphere or this sphere. Okay, but it's no longer in the spherical shape, right? It's more, they're orbiting more in this dumbbell shape. And they can be found anywhere in that space. Okay? If they're in the first p orbital. Look at how many p orbitals there are. 3. There are 3 p orbitals. Now let me explain something about the periodic table. The periodic table is organized according to the SPD orbitals. So if I am in principal energy level 1, and I am in the S sub-energy level, I am hydrogen or helium. Electrons pair. They come in pairs. Hydrogen and helium would be over here for this purpose, are in this first 2 columns of the periodic table, which are the S's. So, potassium is in the 4th principal energy level, sub-energy level, S. Calcium is in the 4th principal energy level, sub-energy level, S. What is cesium in? 6S. Beryllium? 2S. This is the P sub-energy level. Nitrogen is in the 2nd principal energy level, sub-energy level, N. P. What am I talking about? N. Thank you. P. 2P. That was weird. 2P. 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 Okay? My high schoolers love that. 2P. 2P. P. 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 They're like, P. 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 Mr. Crandall. So dumb. Okay? So this is the P sub-energy level.
The whole box.
This whole box. So what is this? Excluding helium. Helium's right here. He's an S. Okay? Bromine. Where is it located? 4P. This is not the 4th energy level, but this sub-energy level right here is the sub-energy level D. We'll talk about the principal energy level. It's in later. But these are all D electrons. Now, look at how many orbitals you have in D. How many are there? 1, 2, 3, 4, 5 orbitals. How many electrons are in a D? 10. How many electrons go into a single orbital? 2. How many orbitals do you have for the P's? 3 orbitals. How many electrons are in each one? 2, because I have 1, 2, 3, 4, 5, 6 electrons. How many orbitals are there for an S? 1. How many electrons fill it? 2 electrons. Electrons pair. That's what they do. They do not like to be alone. If they are alone, they go try to find somebody to pair with. That's what makes them reactive. Sounds like a love story, right? Okay? So, yeah, let's go get a beer. So, they try to find somebody to pair with. Okay? That's what they do. So, oxygen has 2 unpaired electrons, right? Has 2 unpaired electrons, oxygen. So, what is it going to do? It's going to gain 2 electrons so that it'll have all of its electrons paired by stealing them from something else. And now it has paired electrons. Okay? So, what makes an element reactive? Unpaired electrons. These guys right here, they're not reactive. Why? Because they don't have unpaired electrons. They are completely satisfied with just the way they are. Their orbitals are full, and they don't have any unpaired electrons in their orbitals. That makes them very happy. And so, neon gas, it's inert. It's not going to react with stuff. Okay? Yeah, you can excite the electrons and make it glow, but that's about all you can do to it. Okay? The F, sub-energy level. Here's F. How many orbitals are in the F sub-energy level? 7. How many electrons are found in the F? 7 times 2, 14. Yeah, there's 15 here. That's because they took one down from here. Okay? So one of these belongs up here. These two. They belong right here. Okay? So there's 14 electrons in the F. Okay? That's how your periodic table is organized, according to the sub and principal energy levels that these electrons are found. Okay? So we'll talk more about that next time. See you guys.